Hello everyone, it is Buket from ICHEC. This is a short introduction to OpenMP. In this presentation, I will be talking about the topics listed in the outline, which mainly focuses on the fundamental concepts. First, I'm going to define what is OpenMP and talk a little bit about the history of OpenMP. Then I am going to describe a couple of OpenMP terms that you will frequently hear during presentation. Then I will talk about the OpenMP programming model and main components of OpenMP, such as compiler directives and runtime library functions. After that, I'm going to define the OpenMP parallel construct and some worksharing constructs. I will also define a number of data clauses used within these constructs. What is OpenMP? First of all, OpenMP stands for Open Specifications for Multiprocessing. It is simply an application programming interface designed for shared memory parallel computing. It is an open standard developed for portable and scalable parallel programming. It is easy to implement with a high-level and flexible interface. It is a specification for a set of compiler directives, library routines, and environment variables attached to C, C++, and Fortran codes. OpenMP was first introduced in October 1997 for Fortran by the OpenMP Architecture Review Board. After two revisions, version 2.0 was released in November 2000. It was developed for C, C++ in October 1998. Its revised version was released in March 2002. Since 2005, they have been released together, and the first combined C, C++ Fortran version was version 2.5. The next version, 3.0, was released in 2008 with a number of new features and capabilities such as task parallelism. Later in 2011, version 3.1 was released with some minor corrections to the previous version and a couple of new features. In November 2012, the first draft of version 4.0 was released for public comment. The OpenMP Architecture Board plans to release the second draft in the early 2013. You can check the official website openmp.org for updates. This presentation will be about the main properties of OpenMP. The new features of version 3.0 and later will be covered in another presentation. Here is a list of some main OpenMP terms. To begin with, an OpenMP thread is the smallest independent unit of execution with a stack and an associated static memory. It can be thought of as a lightweight process. A set of threads that cooperate on the same task is called a thread team. A thread that coordinates the thread team is called the master thread. It is always the one with ID equal to 0. If a routine is executed correctly by multiple threads, then it is called a thread-safe routine. This is a required property by the OpenMP standard. In OpenMP, parallelization is exploited by a set of compiler directives. An OpenMP directive is a special line of source code with meaning only to compilers that support OpenMP. Executable compiler directives are called OpenMP constructs. Within a construct, an OpenMP clause is used to specify the scope attributes of variables. Let's talk a little bit about the programming model. OpenMP is designed for multiprocessor or multi-core shared memory systems. It relies on different threads running on different processors or cores on the system. Each of these has an access to the shared memory. The underlying architecture can be either a uniform memory access, or non-uniform memory access. In particular, on a non-uniform memory access system, a very fast communication network and special memory addressing allows all memory to be shared. OpenMP execution model is based on the idea of creating and using multiple threads to accomplish parallelism. Most OpenMP parallelism is controlled through the use of compiler directives. It is an explicit parallelism in OpenMP so that it can be as simple as first taking a sequential program and then inserting a set of compiler directives to it. OpenMP uses the fork and join model to create multi-threaded applications. In this model, when the program begins execution, only the master thread is active. The master thread executes sequentially until the first parallel region construct is encountered. At this point, it forks additional threads. The master thread and new threads work concurrently through the parallel region as a team. When the team threads complete the statements in the parallel region, they synchronize and terminate, leaving only the master thread. The number of parallel regions can be arbitrary, and the number of threads can be dynamically updated for different parallel regions. It also supports the placement of parallel regions inside other parallel region. All OpenMP threads have access to the shared memory. They have also access to another type of memory, the private memory, that is not accessed by other threads. They store and retrieve their private data here. Threads communicate by sharing variables. If multiple threads attempt to update the same memory location, data race condition may occur. In this case, synchronization is used to protect shared data from such a race condition. Moreover, threads can cache variables, so they avoid going to memory for every reference to a variable. The values in the cache are not required to be consistent with the values in the shared memory all the time. If needed, the OpenMP flash operation is used in order to enforce consistency. Now we will be getting started with programming in OpenMP. In this context, we first introduce the compiler directives and some general syntax. Compiler directives appear as commands in the source code, and they are ignored by compilers unless appropriate OpenMP flags are specified. They are used for various purposes, such as starting a parallel region or doing the work among multiple threads. The main OpenMP constructs are parallel, worksharing, and synchronization constructs, and data scope attribute clauses. In C, C++, all OpenMP directives are specified by using #pragma-omp. After the pragma and before any clause, a valid OpenMP directive is specified. Clauses are optional and can be in any order. In Fortran, OpenMP directives depend upon the type of Fortran source. For free form source, $OMP is used. For fixed form source, any of these three sentinels at the bottom is accepted. OpenMP directives are case-sensitive for C++ and case-insensitive for Fortran. OpenMP directives only affect the next single statement. To extend the effects to multiple statements, curly brackets are used in C++, and in Fortran, such directives come in pairs and require the AND directive. Throughout the presentation, we illustrate C and Fortran freeform source codes. Several compilers from various vendors support OpenMP. The table here shows what to use for Intel, GNU, and PGI compilers. For Intel, -OpenMP flag is used. For GNU, -f OpenMP, and for PGI, -MP is used. For a full list of compilers and the corresponding OpenMP flag, you can see the link down here. Other main components of OpenMP are runtime library functions and environment variables. These are used to control the parallel program and manage the number of threads. The runtime library functions dynamically control the parallelism during the execution. For instance, OMP set num threads is used to set the number of threads for a parallel region, where n denotes the total number of threads. OMP get num threads is used to get the number of threads inside the parallel region. In order to use these function calls, include omp.h in C++ and specify use omp_lib in Fortran. Many of the runtime library functions have corresponding environment variables that can be set as defaults. These are set from the command line before the execution, and they are valid during the execution unless changed by a runtime library function. For instance, OMP num threads sets the default number of threads to use during the execution. Next, we will be discussing the main constructs of OpenMP. The parallel construct is the fundamental and the most important construct in OpenMP. It forms a team of threads for parallel execution. OpenMP threads are created with the OMP parallel in C++ and Fortran programs. Recall the fork and join model described before. The program begins execution sequentially with the master thread. When a parallel region is encountered in the program, the master thread creates a thread team. Every thread in the team, including the master thread, executes the same statements which are inside the parallel region simultaneously. At the end of the parallel region, the master thread waits for other threads to finish. It then continues executing the next statements. As an illustration, we create a 4-thread parallel region. Each thread executes the code within the parallel region at the same time. In particular, threads with thread IDs from 0 to 3 simultaneously call the function foo with the input parameters thread ID and the A vector. At the end of the parallel region, threads wait for all threads to finish before proceeding. It is sort of an implicit barrier for synchronization at the end. Now look at the simple hello example using OpenMP in C and Fortran. We start by loading the OpenMP library, then we create the parallel region. Inside the parallel region, we call two runtime library functions. The first one is OMP getThreadNow to return the thread ID of each thread, and the second one is OMP getNumThreads to return the total number of threads in the team. We compile the code by Intel compilers, respectively by using -OpenMP flag. Then we set the total number of threads to be executed inside the parallel region by the environment variable OMP numThreads equal to 4. As can be seen from the output, each thread prints hello with their thread IDs and total number of threads. We will now briefly describe some main properties of the parallel construct. First one is dynamic threads. It is used to change the number of threads used in a parallel region during the execution. This is useful as some parallel regions may require more or less threads to be executed than the other regions. This is possible by letting the system choose how many threads execute each parallel region. Note that the number of threads will be equal to or less than that is set by the user, and it remains fixed for the duration of each parallel region. There are two methods available for enabling dynamic parallelism. It is done by either using OMP set dynamic runtime function or setting OMP dynamic environment variable to true. OMP get dynamic runtime function can be used to determine if it is enabled during the execution. Moreover, OpenMP allows to nest parallel regions. A thread within a team of threads inside a parallel region may fork additional threads. The new team will contain only one thread unless nested parallelism is enabled or supported. There are two methods available for enabling nested parallelism. It is done by either using OMP set nested runtime function or setting OMP nested environment variable to true. OMP get nested runtime function can be used to determine if it is enabled or. Two useful clauses that can be defined for the parallel construct are if and nowait clauses. If clause is used to determine if the region should be parallelized. In case the condition evaluates false, the code is executed serially. It can be useful, for example, when data is too small and there is no need for parallelization. You can see in the example above that it checks if n is bigger than 100. Nowait clause is used to remove an implicit barrier. If present, threads don't synchronize at the end of the parallel region. Threads that finish earlier proceed without waiting other threads. In C, C++, it is added after OMP parallel, while in Fortran it is added after OMP and parallel. Now it is time to describe the main data clauses. They are used in conjunction with OpenMP directives to control the scoping of enclosed variables. In OpenMP, it is of vital importance to understand, for instance, how and which variables are transferred to the parallel region. Main data clauses are default, shared, and private. The default status of the variables in the parallel region is defined by the default clause. It can be either shared or private or none. Note that C++ doesn't have private option for the default clause. The shared clause is used for variables that are accessible by all threads in the team. A shared variable is shared among the team threads executing the parallel region. All threads can read or write to that variable. The private clause is used to denote variables private to each thread in the team. A private variable can only be read or written by one thread. The values of a private variable are undefined upon entry to or exit from the specific construct. In OpenMP, most variables are shared by default. For instance, file scope and static variables in C++, common blocks, save and module variables in Fortran. Moreover, dynamically allotted variables are also shared by default in both languages. On the other hand, variables declared in parallel region are always private. In particular, it is a standard that loop indices and temporary variables used inside the loop are defined to be private, while main arrays and read-only variables are defined to be shared. We rewrite the simple hello world example by using data clauses. The variable teeth denotes the thread ID, and threads denotes the total number of threads in the team. Notice that we define a thread ID of each thread as a private data, so there will not be any race condition for this variable. We set the total number of threads as shared data, since it is not a thread-specific value and it is same for all threads. We compile, set the OMP num threads to 4 and execute the program. Then we get the same output as before. Some other useful data clauses are listed here. First private and last private are also commonly used data clauses in OpenMP. They are special cases of the private clause. First private initializes a variable according to the value of the corresponding global variable prior to entry into the parallel region. Last private passes the value of a variable from the last iteration in the parallel region to the corresponding global variable. Thread private is another data clause. It is used to make global data private to thread. It also preserves global scope within each thread. Copying clause is similar to first private for private variables. It copies the thread private variables from master thread to the team threads. Note that no copy out is needed because the value of a thread private variable is maintained throughout the execution of the whole program. There are two more data clauses in OpenMP. They are copy private and reduction. We will discuss them later. Worksharing constructs are used to divide the work among thread teams. They are defined inside a parallel region. They don't create new threads. They are used to indicate what kind of work is to be parallelized. By default, there is an implicit barrier at the end of the work sharing region, since all threads in the region wait for others to finish. Nowait clause can be used to turn off the barrier. We next describe three work sharing constructs. They are sections, single, and workshare. The sections construct is a non-iterative work sharing construct. It specifies enclosed sections that are distributed over the threads in the team. These sections are created with OMP section in C++ and Fortran codes within OMP sections construct. Each specified section is executed by exactly one thread. If there are too many sections, some threads execute more than one section in a round-robin fashion. On the other hand, if there are too few sections, some threads stay idle. We demonstrate the sections construct in our basic Hello World example. We create three section directives that are nested within a sections directive on top. We compile, set the thread number to 4 and execute. It can be seen from the illustration and output on the right hand side that each section is executed exactly once by one thread. The thread ID which executes each section is written in the output. We don't know in advance which thread will execute which section. The single construct specifies a block of code that will be executed by one of the threads in the team. The other threads which don't execute the block wait an implicit barrier at the end of the single construct. It may be useful, for example, when dealing with sections of parallel regions that are not thread safe. Similar to the sections construct, it is defined after OMP parallel in C, C++, and Fortran by using OMP single command. Copy private data clause is associated with the single construct. It is used to broadcast values obtained by a single thread directly to all other threads in the team. Thus, it mustn't be used with the nowait clause. The workshare construct is defined only for Fortran. It is used to divide the execution of the enclosed structured block into separate units of work. Threads of the team share the work. Each unit of work is executed only once by one thread. The workshare construct allows the parallelization of array and scalar assignments, var and for all statements and constructs, parallel and some synchronization constructs. To illustrate, consider parallelization of a simple vector addition program. In this program, we first define the vectors and fill before the parallel construct. The vectors A, B, and C are set as shared so that all threads will access the same data. We use OMP workshare just before the line that applies the vector addition. Then the work will be distributed among the threads in any manner. These are the references used to prepare this presentation. Thank you for your attention.